All right, in this video, I'm going to work through this section 5.5 day 2 handout. It's got a front and back side to it. So I'll zoom in here. And it's assumed that you already worked through the day 1 handout and already seen the introduction to the substitution method where we're working with indefinite integrals. Today we're going to solve definite integrals. That is, we're going to calculate areas under curves using the substitution method. So here's our first example worked out already for us. We're trying to find the area under e to the 5x from x equals 1 to 2. And that's what that definite integral notation means. And we realized in the day 1, we have an inner function. 5x is being plugged into the e to the u function. So we can let u equal to 5x, calculate its derivative with respect to x, so du over dx is 5. And we can solve for dx. That's 1/5 du equals dx. Right, so that's just rearranging our previous equation. And what we're going to do in a moment is replace dx with what we solved for, 1/5 du. But we're going to do one extra thing now, and this is the new part today. Our original limits of integration, x equals 1 and x equals 2, those numbers were x-coordinates. Since we're going to rewrite our integral in terms of u, we want to figure out what x equals 1 and x equals 2 is in terms of u. So we can use our original substitution of u equals 5x and figure out what the corresponding numbers for u are. Well, when x equals 1, u is equal to 5, right? Because 5 times 1 is 5. When x is equal to 2, u is equal to 10, because 5 times 2 is 10. So when we rewrite our integral in terms of u, right, we have 5x being replaced by u, so you get that u there. dx gets replaced by 1/5 du, since we found those were equivalent. Then x equals 1 is equivalent to u is equal to 5. And x is equal to 2 is equivalent to u is equal to 10. Right, so there's several substitutions there. Right, 5x turns into u, dx turns into 1/5 du, and 1 and 2 turn into 5 and 10 respectively. So we get this new integral. Oops, sorry there. We get this new integral that looks easier to solve for because we can just right away say, oh, the antiderivative of e to the u is e to the u, and that 1/5 stays there from the constant multiple rule. So here's the antiderivative in terms of u. Then we just got to plug in u equal to 10 and u equal to 5. So plug in 10, plug in 5, and we're subtracting those antiderivatives when you evaluate at 10 and 5. So you could come up with a rounded answer, but we're just going to leave it in its exact answer form there. 1/5 e to the 10 minus 1/5 e to the 5. That is the area under e to the 5x from x equals 1 to 2. But notice we transformed it to finding the area under e to the u times 1/5 from u equals 5 to 10. Right, so we transformed this integral into something that's simpler to calculate, and we'll see how there's more complex problems on this handout where the substitution will be very helpful to do. Maybe you recognized right away that, oh, if I do reverse chain rule, the antiderivative is 1/5 e to the 5x, then you can plug in 2 and 1, subtract the 2, and you'll get the same answer as this over here. But there'll be other problems that are they're tougher, and you won't be able to just kind of see what the antiderivative is. We'll have to work through this method. All right, so there's our warm-up example. Let's do another one, problem 1. So we have the definite integral of e to the 1 over x divided by x squared dx. So it's the area under this function from x equals 1 to 4. Now we see this inner function 1 over x, so we can let u equal to 1 over x. I'm going to zoom out here a little bit. So u is equal to 1 over x. Can compute the derivative of that, right, from power rule. X to the negative 1's derivative is negative 1 x negative 2, which is the same as negative 1 over x squared. And then I'm going to solve for dx. So negative x squared du is equal to dx, right? So that's rearranging this equation to solve for dx. Multiply dx over to the right, multiply x squared to the left, and also that negative sign. And so eventually I'll be able to replace dx with negative x squared du, right? Because they're equivalent. We can replace one with another. But I'm going to do a little bit more work, just like in that warm-up example. I'll say also x is equal to 1 means u is equal to 1 over 1, right? Based on our substitution. So u and x are the same there, but when x is equal to 4, our upper limit, well, the corresponding number for u is 1 over 4 based on the relationship between u and x. That will allow us to write the entire integral in terms of u, right? We need to switch these limits of integration. So that's the new part for this handout compared to the day 1 handout. So we can rewrite this integral instead from 1 to 4. We can write from 1 to 1/4. And e to the 1 over x turns into e to the u, since 1 over x is u. We have divide by x squared still, and dx can also get replaced with negative x squared du. All right. Notice the x squareds cancel. So you can rewrite this integral as 1 to 1/4 e to the u. I'll put that negative sign out front. Okay. Notice we transformed what started off as a really messy integral. We did a few substitutions, and we got this very nice, simpler integral, because we know the way to solve this is, find the antiderivative, right? This is the fundamental theorem of calculus. It says to find the area under negative e to the u from 1 to 1/4. We'll find the antiderivative. That's negative e to the u. Then we plug in a 4th and 1 and subtract the 2. So you get negative e to the 1/4. So that's when you plug in a 4th. Subtract when you plug in 1. Right? So plug in a 4th, plug in 1, subtract the 2. And you have to be careful, use parentheses, right? Because you have a negative, negative. So just be careful with the negatives there. So you could rewrite this as a plus e, right? E to the 1 is e. So that is the area under the original function we're looking at from x equals 1 to 4, which is the same thing after substitution as the area under negative e to the u from 1 to 1/4. All right, next example. We see this inner function 1 plus 7x. So it'd be nice to replace that inner function with a u. So I'm going to say u is equal to 1 plus 7x. And the derivative of that with respect to x is just 7. So I'm going to solve for dx. 1/7 du is equal to dx. And also remember, I need to change my limits of integration to be in terms of u. So also, when x is 0, u is equal to, well, from our u equals x equation, it's 1 plus 7 times 0, it's just 1. And when x is equal to 1, u is equal to 1 plus 7 times 1, that's 8. All right, we have everything we need to do our substitutions. This integral can get transformed into the integral. Instead of x equals 0 to 1, we now have u equals 1 to 8. Instead of 1 plus 7x, we have u, so the square root of u now. And dx we found to be 1/7 du. All right, so we transformed a messy integral into a simpler one through substitutions. Right? We replace things that are equal to each other, so we're not changing the final answer. And we do the antiderivative of the square root of u. Right? U to the 1/2 turns into u to the 3/2 over 3/2, or I can say times multiplied by 2/3 instead. So have that times 1/7. Gotta plug in 8, plug in 1. So we have 8 to the 3/2 over 3/2 times a 7th minus, plug in 1, 1 to the 3/2 over 3/2 times 1/7. So whatever that comes out to be, right, you can simplify on your own. I'm just going to leave it like that. But that is the area under the square root of 1 plus 7x from 0 to 1. Right? We use a substitution method along with the fundamental theorem of calculus, which says to find the area, you can just use the antiderivative. And there you go. So one common question is, in day 1 of the substitution method, when we got our antiderivative in terms of u, we then resubstituted the 1 plus 7x back in. Well, you don't need to do that because we changed our limits of integration to be in terms of u. So you can just plug in those u numbers in, the 8 and 1. No need to go back to 1 plus 7x. If you did go back to 1 plus 7x, then you have to plug in your numbers for x, that 0 and 1. So you kind of be doing extra work there. So no need to put the 1 plus 7x back in to your antiderivative at the end, because we already changed our numbers to be in terms of u instead of x. Okay, let's move on. Find the area under sine of pi x from 0 to 1. Well, we have this inner function of pi x. So say u is equal to pi x. That way we can eventually rewrite our integral as sine of u. But we need to replace the dx, so the derivative of du with respect to x is pi. Can solve for dx as 1 over pi du is equal to dx. And also, let's change or figure out what the numbers are for u when x is 0. U is equal to pi times 0 is 0, so that stays the same. But the upper limit does change. Plug in 1, you get pi. So you can rewrite this integral as the integral from 0 to pi now, right? Because that's in terms of u. Sine, instead of pi x, it's sine of u, since pi x is equal to u. And dx is equal to 1 over pi du. So you can replace dx with what it's equal to. The antiderivative of sine is negative cosine of u. So have that constant multiple of 1 over pi. Right, that just stays there. Plug in pi, plug in 0. So negative cosine of pi times 1 over pi minus negative cosine of 0 times 1 over pi. All right, cosine of pi is negative 1. So you get a negative 1. So that turns to positive 1 over pi. So 1 over pi. Then you have a minus minus, so that's positive. Cosine of 0 is 1. So you get plus 1 over pi. That's 2 over pi. 2 divided by pi is the area under sine of pi x from 0 to 1, which is also the area under sine of u times 1 over pi from 0 to pi, right? Because we made the switches so that the integral was nice and quick to compute. All right. Stop the video anytime you need to look at the math in more detail to see what happened. All right. Problem 4. I'm not really seeing an inner function when I look at this. So you could make some guesses and try, and if it doesn't work out, try another thing to be equal to u. But one thing that you can kind of foreshadow is if I did make u equal to natural log of x, when I take its derivative, I would get 1 over x. And I see 1 over x in this function here. Right? I would divide by x. So let's let u equal to natural log of x, because the derivative we see in our integrand. Derivative of natural log is 1 over x. So we can solve for dx as x du is equal to dx. Also, when x is equal to 1, that means u is equal to natural log of 1, which is 0. And when x is equal to e, that means u is equal to natural log of e is 1. So the limits of integration change to become 0 and 1. So if the integral from 0 to 1 of natural log of x, well, that's equal to u. So natural log of x gets replaced by what's equal to. We still have divided by x. And then dx we found to be x du. So the x's cancel. You can rewrite this as the integral of u from 0 to 1, which is u squared over 2, plug in 1, plug in 0. Wait, that's how you find the area under u from 0 to 1. Use the antiderivative. That's the fundamental theorem of calculus. You get 1/2. 1/2 is the area from 1 to e under natural log of x over x. All right, number 5. Again, I don't see an inner function, but it would be nice if this at least looked like 1 over u instead of 1 over 3 minus x, because I know the antiderivative of 1 over u is natural log of the absolute value of u. So let's try that out. Let u equal to 3 minus x. Its derivative is -1. That means negative du is equal to dx. Also, when x is equal to 4, what is u? Well, u is equal to 3 minus 4, so u equals -1. And when x is equal to 8, u is equal to, well, plug in 8, 3 minus 8, -5. All right, so we're going to rewrite this integral. Instead of 4, we have -1. Instead of 8, we have -5. And then we have 1 divided by 3 minus x. But 3 minus x is what we let u be equal to. And dx is equal to -du. So -1 du. All right. The antiderivative of 1 over u is natural log of absolute value of u. And we still have that times -1 as that constant multiple. Let's put that out front. Negative natural log of absolute value of u. We got to plug in -5, plug in -1, subtract the 2. So negative natural log of the absolute value of -5 minus, plug in -1, negative natural log of absolute value -1. That's negative natural log of 5. Minus minus is a plus. Natural log of 1. Natural log of 1 is 0. So this being negative natural log of 5. All right, again, stop the video. Just take your time to see all the substitutions happening. And the main idea is we're transforming something that we can't see the antiderivative immediately. So we do these steps of substitution so that we eventually transform into an integral that we can see. Oh, I can use the antiderivative of 1 over u to find the area under the curve. And the new thing today is that we're also switching the limits of integration, because we're working with definite integrals. Day 1, we're working with indefinite integrals, whether we're no numbers to switch, because an indefinite integral is just the antiderivative of the function. So when you have a definite integral, we're actually finding the area as our final answer, which is a number. All right, problem 6 looks pretty similar to problem 5, but this time we have an x plus 1 on the top. Let's use problem 5 as our motivation for choosing u to be the denominator again because it worked out nice, right? This one's hard to tell. We could try letting the x plus 1 be equal to u, do some of our math steps, and it would be pretty tough to do that way. So if you were just doing trial and error, that's fine. Next, try 3 minus x is u. We saw it work nicely in number 5, so let's do that again. Let's use the denominator to be u. So another reason why we'd want to transform the bottom into u, oops, sorry, let me zoom back out, is if that did turn into u, you could split that fraction into multiple pieces, right? Because you'd have a single divided by u, and you could split into multiple fractions. So we'll see that coming up too. Okay, derivative again is -1. So negative du is equal to dx if you rearrange that equation. All right, eventually we can replace dx with negative du, but not yet. Let's change the limits of integration. Also, it's the new thing today. When x is 4, again, we have u is equal to -1. And so same thing as last time. It's -5. When you plug 8 into our relationship, so you might say it's -5. So I can rewrite my messy integral as the integral from, instead of 4 to 8, it's -1 to -5. And then the 3 minus x turns into a u, because u is equal to 3 minus x. Just have the x plus 1 on the top. And then dx is equal to negative du. So negative times negative du. I'm going to put that negative somewhere else. I'll put it on the, so I'll distribute it through the numerator, so I have negative x minus 1 instead of x plus 1. Okay. So I still have an x in this, and I don't want an x in there because I want to use my fundamental theorem of calculus to take the antiderivative purely in terms of u, but I still have an x in here, so that's a problem. So think about how you can get rid of that x for a moment. The way you do that is rearrange your relationship between u and x. We add the x to the left, subtract the u over, and you can replace that x with 3 minus u. So let me highlight that in red. We've got this is equal to the integral from -1 to -5. Minus x is now -3 minus u. So that -1. Okay, so that was x. Got turned into 3 minus u. So divide by u. And before we do the antiderivative, let's just simplify this fraction quite a bit. So distribute that minus sign through, you get minus 3 plus u, and then -1. So you really have u minus 4 over u du. So -3 minus 1 is -4, minus u is plus u. So that's what it turns into. Then we split this into 2 fractions, right, with the common denominator of u. So u over u minus 4 over u. My 4 looks like a u, 4 over u. Du. And u over u is just 1. So I have 1 minus 4 over u. We know the antiderivative of 1, that's u. Antiderivative 4 over u is 4 natural log of u. Right? So use the fundamental theorem of calculus, take the antiderivative, get u minus 4 natural log of absolute value of u. That's my antiderivative. I'm going to plug in -5, plug in -1. And I'll let you do the rest of that one, right? Because it's kind of plug and chug. Plug in -5 and plug in -1 and subtract the 2. All right, so that one was a little longer to solve. Last problem here. Breathing is a cyclic in a full respiratory cycle from beginning of inhalation to end of exhalation takes about 5 seconds. Right, so take a deep breath. Right, when you're breathing, It's cyclic. You breathe in, then you breathe out, and it cycles over and over again, in, out, in, out. If you take a breath, right, it takes about 5 seconds from the start of inhaling to the end of exhaling. It's a full cycle. The maximum rate of airflow into the lungs is 0.5 liters per second. So this is kind of on average for a person. That's how many liters per second are going into your lungs at maximum. It's the fastest it's going in. The function f of t equals 1/2 sine of 2 pi t divided by 5. It's often used to model the rate of air flowing into the lungs. So this is a function that describes how fast the air is flowing into the lungs. You notice this matches up with the previous sentence. The biggest this can get is 1/2, because the biggest sine can get is 1. Right? Sine oscillates between -1 and 1. So the biggest it gets is 1. So the biggest f of t overall gets is 1/2, which is exactly what was just said. Okay, so this is describing how fast the air is flowing in liters per second. So use this model to find the volume of inhaled air in the lungs during 1/2 cycle. So just when you're breathing in, how much air is flowed in. If you did a full cycle, it'd be a net air of 0 because you inhaled and exhaled. So that would be the area under this from 0 to 5. You'd find to be 0. The positive area will exactly cancel with the negative area. But we're just looking at the inhale. So from 0 to 2.5. So the integral from 0 to 2.5 of 1/2 sine of 2 pi t divided by 5 dt. So why are we even doing an integral given the sentences here? It's because we're given a rate function. And we learned if we find the area under a rate function from time equals a to b, we'll find the net change in this case, of volume, right? Because this is essentially the derivative of volume. Do the integral, or the antiderivative is the method to find the integral. Do the antiderivative of a derivative, you'll get the net change in the thing you're taking the derivative of, that is volume, right? So this is a net change theorem application using the substitution method. Another way to think about it is if you graph this, right, that's a volumetric rate plotted against time. Find the area under that, you'll get volume, right? The volume accumulated in your lungs. Okay, anyways, this is something that we can't just right away say, oh, here's the antiderivative, and I'll plug in 2.5 and 0 and subtract the 2, right? Because we have a messy function, so the substitution method helps us to simplify the integral. In this case, we see an inner function of 2 pi t over 5. So you can say, oh, I let u equal to that inner function. Take the derivative of u with respect to t. In this case, you get 2 pi over 5. That's the derivative of that. Solve for dt. So 5 over 2 pi du is equal to dt. Also, when t is equal to 0, well, u is also equal to 0 based on our relationship between u and t. But when t is equal to 2.5, let's see, u equals, plug in 2.5, you get 2 times 2.5 is 5 divided by 5, you get pi. So you get pi from that relationship. So you can rewrite this integral as the integral from 0 to pi, instead of 0 to 2.5, it's 0 to pi, since we're writing in terms of u. 1/2 sine of u, since the inner stuff we let equal to u, and dt is equal to 5 over 2 pi du. All right, we can simplify it a little bit. This is the integral of 5 over 4 pi times sine of u du from 0 to pi, which is that constant multiple stays there. Antiderivative sign is negative cosine, so I'll put the negative up front. Cosine of u. Plug in u is equal to pi. Plug in u is equal to 0. And subtract the two. Cosine of pi is -1. Cosine of 0 is 1. So you get a negative 5 over 4 pi minus a negative. So there's a lot of negatives going on. Let's see, you get 5 over 4 pi. And you plug in pi. And you subtract. When you plug in 0, you have a negative again. So 5 over 4 pi. Looks like you get 10 over 4 pi. That's the amount of liters that you inhale into your lungs on average. All right, well, that's it for this handout. Again, the main idea is we're simplifying a messy integral into something simpler by the use of substitutions. And the difference with day 2 in comparison to day 1 is we're working with definite integrals instead of indefinite integrals. So we have these limits of integration that we need to change to be in terms of u. And that's kind of the extra layer so that we can find areas under curves when the functions are messy. All right, hopefully that video was a good one for you, and have a good day. Bye.